For fluid systems, or we mean by fluid systems we mean gases or liquids जिसमें वॉल्यूम चेंज हो जाता हो, जिस पे प्रेशर पड़ने से वॉल्यूम चेंज हो जाता हो, जिसमें उसके अलावा बाकी थर्मोडायनामिक पैरामीटर्स भी चेंज होते हैं. So for them we have some relations, if you recall. Cp minus Cv being equal to T times V times alpha P squared over isothermal compressibility. And we also had another relationship, kappa S minus kappa T equal to T times V times alpha P squared over heat capacity at constant pressure. क्या हुआ? हैं? ये पेपर में आया था ना? आपको मालूम था, वो पेपर भी दे दिया हैं? ये देखें, इसी वजह से आपके टीएस परेशान थे कि जो पढ़ाया है क्लास में वो आप पेपर में दे रहे हैं. All right. So this is the other relationship, and of course all of you solved it. All of you had a good time solving this, and together we have the relationship Cp over Cv is the ratio of heat capacity of compressibilities. These relations among the 4 response functions, 5 response functions, in fact, these 3 relations, reduce them to only 3 independent. They actually, one of them is obtained from the other 2, and therefore you cannot say that you have 5 response functions and 3 equations, and therefore there should be 2 independent response functions left. That is not the case. The third one is actually obtained from here, or this is obtained from here, whichever way you see it. So there are at least three independent response functions. That is one thing that I think I said the last time, but I didn't emphasize is enough last time. All response functions are positive definite quantities. But positive definite quantities in in a state of equilibrium. So that if a system is in a state of equilibrium, all of these quantities are positive definite. So if alpha p is defined as 1 over v times partial differential of v with respect to t at constant pressure, then it is definite that when you increase temperature, volume will also increase with it. Okay, increasing temperature will increase volume, which is a normal experience also. But this normal experience is normally seen in the state of equilibrium of systems. In a stable state of equilibrium, I will put a word over here, in a stable state of equilibrium. Similarly, if kappa T is given as minus 1 over V dV by dP at constant T, then in a normal stable state of equilibrium, when you increase pressure on a gas, volume must decrease.
So don't we call the equilibrium a stable state? What do you mean by stable state of equilibrium?
Okay, I will have to define these things: stable state of equilibrium and what do you mean by stable state of equilibrium. And I think they will in a couple of lectures after this, we will get into discussing stability of equilibrium states. Okay, and then we will get to see what we mean by it. But briefly, when we define a state of equilibrium, we say we leave the system to where it is; it will remain there for as long as it is not disturbed. So that we define as a state of equilibrium. Or we take a system and disturb it, and if the system goes back to the original state, then the original state is a stable state of equilibrium. So if I have a curved surface like this, for example a ball, and I put a ball in it, then this ball will always remain here. I disturb it, take it up there, it will come back to this particular position, right? So this particular state is a state of equilibrium for it, and a stable state of equilibrium for it. But if I put a piece of chalk over here and I disturb it, it will always find another state, equally probable state. It will not come back to this original state. So this state where it is now is not a stable state of equilibrium. It is a state of equilibrium for it because you leave it and it will be there. But if you disturb it, it will not necessarily come back to the original state. If it doesn't come back to its original state upon disturbing it, then it is not a stable state of equilibrium.
So the original position is not a stable state of
original position or the other positions, but it can't be brought to any. So this is the stable state of equilibrium, and the conditions that we say over here are therefore describe what happens if your system is undergoing a change in its state of equilibrium. So in a change of state of equilibrium, they may not remain positive definite. So positive definite, they will change sign, and I think this will be a criterion that we will use when we discuss stability of states and stability of equilibrium states. But that will come a couple of lectures away, couple of lectures later. Yeah, sorry.
So kindly बता देंगे 3 independent response functions.
अगर आपके पास 5-6 वेरिएबल हों और 2-3 इक्वेशंस हों तो इंडिपेंडेंट वेरिएबल्स कम हो जाते हैं ना उन इक्वेशंस की वजह से. यही मेरा मतलब यहाँ पे भी है इनके साथ कि there are 5 response functions, and if there are well, I said there are not actually 2 equations, 3 equations, but only 2 equations. The third is a consequence of the 2 equations. तो उसकी वजह से 3 response functions independently बच जाते हैं. ये मतलब. Okay. So we will come to discuss this stability of states a little more मैंने इससे पहले आप लोगों को जो ये एक्सरसाइज करवाई थी, आई होप आई कैन गेट टू दैट पीस ऑफ पेपर क्विकली. मैंने जो आप लोगों को ये एक्सरसाइज करवाई थी कि इसमें जो मैंने प्रैक्टिस क्वेश्चंस करवाए थे, तो उनमें से 3 तो यहाँ हमने कर लिए थे, 2 मैंने आप लोगों को छोड़ दिए थे, और मैंने मेरे पास आप में से कई लोग आए थे उसको डिस्कस करने के लिए. तो आप लोगों ने, मुझे मालूम है कि आप लोगों ने इनके ऊपर बाकी 2 सवालों को भी आप लोगों ने वर्कआउट कर लिया था. उनमें ख़ास बात यह है कि अगर आप मिसाल के तौर पे जूल-थॉम्सन एक्सपेंशन को देखें, जूल-थॉम्सन एक्सपेंशन टेक्स प्लेस अंडर द कंडीशन ऑफ no change in enthalpy. So find the change in pressure as temperature is lower. So if you have to look for, you see, let me take it from the point of view of change in temperature as a function of change in pressure, and this change takes place under the condition that enthalpy remains constant. Okay? This is what was stated in this question. Although I said find the change in pressure as temperature is lower, but let me take it to describe change in temperature as pressure is increased or decreased, or and of course, if you're talking of Joule-Thomson expansion, then what we mean actually over here is that this quantity is called mu. The symbol given to it is mu literature in the literature, perhaps because Joule and Thomson gave this symbol to it with a subscript h associated with it, so that people will write it as dt equal to mu h times dp, or you will say mu h is dt by dp at constant h. And Joule-Thomson experiment, you remember it from your old days, right? Let me see if I remember it. Joule-Thomson experiment was actually नहीं, मुझे अभी याद नहीं कि मैं थॉम्सन एक्सपेरिमेंट, जूल एक्सपेरिमेंट की बात कर रहा हूँ या जूल थॉम्सन की बात कर रहा हूँ. आई कैन नॉट बी सो श्योर. No, I will not confuse you with the description of this. Let us remain confined to this expression and work it out. You worked it out yourself, but let me try it here. We said that this is something which can be easily worked out if all the energy, whatever energy function appears as constant, is brought to the numerator, right? Entropy or energy function is brought to the numerator. So this is when you bring it to the numerator, and that is by using this rule. So dH by dt at constant p is what this is about. And then you say that dH by, since dH is equal to t times ds plus v times dp, right? So by now you all remember each one of these relations, right? By heart. So before I even write, you just have it at the tip of your tongue. dH is equal to TdS plus VdP, so that partial differential of H with respect to P at constant T is equal to, I will divide this, I will take dH equal to TdS plus VdP, and I will divide it by P, dP, dP and dP, and I will take T constant and T constant and T constant, and this of course is 1. So I have this TdS, T times ds by, so this is equal to T times ds by dP at constant T plus V. And ds by dP at constant T happens to be minus by Maxwell, its Maxwell equivalent is dV by dt at constant P, easily, this plus V. Alright, so this is the expression, and this I can write also as minus T times V times alpha P plus V. This is what goes in the numerator, and the denominator, if I follow the same procedure, if I write dH equal to TdS plus VdP, and I will say for this divide by dt, divide by dt and divide by dt, and I take constant P and constant P and constant P, then this vanishes, and what you get is that this is equal to TdS by dt at constant P is Cp. So the whole thing, Joule-Thomson expression mu equal to mu h equal to dt by dP at constant h is equal to minus, the numerator is minus T times V times alpha P plus V, and denominator is Cp. Okay, and that is equal to, you take minus sign and V and everything out, this is V over Cp times T alpha P minus 1. And this is where you noted that in the case of ideal gas, mu h is equal to 0. Because in the case of ideal gas, alpha P is equal to 1 over T. Right? In the case of ideal gas, alpha P is equal to alpha P is equal to 1 over T for ideal gas. I'm sorry? गलत कर गया मैं ये काम? ठीक होगा, देख लेना जरा. So that actually tells you that therefore for ideal gas, mu h is equal to 0. मैं गलती तो नहीं, मैं देख लूँ, आप लोग बहुत परेशान हैं. ये माइनस साइन बाहर है वैसे ही, और ये क्वांटिटी मैंने कहा था कि दिस इज इक्वल टू दिस क्वांटिटी, सो इट इज देयर. और ये नीचे वाली क्वांटिटी है उसके बारे में मैंने कहा था इक्वल टू Cp. सो ये लिखा हुआ ठीक है, ये ठीक लिखा हुआ है. तो क्या गड़बड़ हो गई? आप लोग परेशान क्यों लगे?
सर ये
Okay. So this is the expression, and it tells you that this is equal to 0 for an ideal gas. And for that, and on the other hand, if the Joule-Thomson expansion has to actually, with increasing, if you expansion, Joule-Thomson expansion would mean that dP is negative. Expansion means final pressure is lower than the initial pressure. Okay? And dP is negative, and therefore, in terms of mu, which is partial differential of T with respect to P at constant H, this quantity, if this is expansion, dP is negative. dP means P final minus P initial. Then cooling would amount to dt being also negative. Tf minus Ti is negative. So mu must be positive. For cooling to occur. All right? And that requires that V times alpha P be greater than 1. So if V times alpha P is greater than 1, then we make sure that mu is a positive quantity and cooling will indeed take place. Okay? ठीक है? कोई सवाल इसके अलावा? ठीक है?
सर ये किसी भी गैस के लिए या सिर्फ आइडियल के लिए
नहीं, आइडियल के लिए जो 0 है वो तो पहले लिख दिया मैंने यहाँ पर. Alright? This is for a real gas. So this is where we have still not used the property that in a change that all the response functions are positive definite. We will have some situations, some examples where the positivity of response functions will indeed this could never be possible had there been alpha p being a negative quantity. ये बात ठीक है ना? I'm sorry?
So जो definite आप लगा रहे हैं positive के बाद इसका क्या मतलब?
Oh, positive definite का मतलब एक under okay, whatever the value of other parameters. Okay? Okay, so you can be sure that this is going to be positive quantity. इसमें एक खास बात जो है वो ये कि if V alpha P is greater than 1, then certainly alpha P is a positive quantity. कि alpha P अगर negative होता तो फिर कभी नहीं हो सकता था ये.
V alpha P आया कहाँ से?
V alpha P तो यहाँ से, और ये कहाँ से आया? वो यहाँ से आया, वो यहाँ से आया.
T alpha P नहीं?
हाँ?
T alpha P.
अच्छा, I'm sorry. Okay. Sorry. T alpha P. Yeah, I'm sorry. T alpha P. T alpha P is greater than 1, and because T is always a positive quantity, alpha P definitely shows it's a positive quantity, and therefore this is this again shows that this would not have been possible had that not been true, that all the response functions are positive quantities. Okay. There was the other one also about the internal energy remaining constant, and that actually leads to a fairly involved function, which I can work through that also, but that may not quite give any new insight into the thing. All right. Let me now talk of something a little different. We have spoken of equilibrium states.
कौन से टेम्परेचर वॉल्यूम है इनिशियल या फाइनल.
Okay, normally what you do is that when you have this value, you will not put in the value right there. What you will do is you will integrate this equation. You will integrate which equation? कहाँ रखी है equation? ये वो equation जो लिखी है ना, ये वाली equation. You will integrate this equation. You will substitute for mu h into this equation, and you will integrate this equation. You will substitute this expression into this and integrate this equation. And when you integrate, then what you do is you will take all the t onto the other side and all the p on the other side, and if you get v, then you will use some equation of state. And obviously you will not use ideal gas equation of state, because for ideal gas this we already saw that this is equal to 0. So this is going to be for a real gas, and then you will do the integration, and integration will be from T1 to T2 and P1 to P2. Okay? Equilibrium states, and when I talk of I intend to define different equilibrium situations. The first one is thermal equilibrium. And you can isolate different kinds of equilibria from each other, and you can create laboratory situations where you can study different kinds of equilibria with respect to each other. So this will be more like having a system with two components of the system, and these two components of the system are separated by a wall. This wall, separating wall between two systems or two components of the same system, and this wall you define as being, number one, diathermal. Diathermal means that which allows heat to pass through, and rigid, that it can't move, no change in volume of the two components, and number three, impermeable for particles, and therefore particles cannot be exchanged between the two portions. So the only thing that can happen when these systems क्या हुआ? अच्छा. The only thing that can happen is that the systems can exchange heat with each other, energy with respect with each other. Heat can be exchanged, and this heat can be exchanged until systems come into equilibrium with each other. And the equilibrium which they can have with respect to each other will be thermal equilibrium, because it has been isolated from other equilibrium states. And this thermal equilibrium will be thermal equilibrium or energy flow or heat flows due to the heat can flow only if there is a temperature difference. If there is no temperature difference, heat cannot flow. And when the heat flows between the two systems because of temperature difference, it flows in to equate temperatures. So there's a difference of temperatures, and because of the difference of temperature, heat would flow from higher temperature to lower temperature compartment, and the purpose of this will be to increase the temperature of the compartment at lower temperature and reduce the temperature of the other compartment. And therefore it goes into equate temperatures. And this is how thermal equilibrium is achieved. So thermal equilibrium is signaled or is guaranteed by equation of equality of temperatures. Thermal equilibrium is equality of temperature. And when the temperatures are equal, then heat will stop flowing, and the two systems will be in two subsystems or two systems will be in equilibrium with each other. Compared to this, we can speak of mechanical equilibrium, in which the wall will have some different properties. Number one, we want to isolate it from thermal equilibrium, so we will say this wall wouldn't allow heat to flow, so it will be adiabatic wall. Number two, it will be a non-rigid wall. It can slide, it can move, it can therefore, because of this sliding of the wall, volumes of the two parts can change. And the third thing is it will be still impermeable, so that matter is still not allowed to go through. In this way we isolate mechanical equilibrium from thermal equilibrium and the third equilibrium that I will talk about in a minute. And wall will slide if there is a pressure difference across the wall.
So can we achieve one state of equilibrium due to another? Can we achieve temperature equilibrium due to mechanical equilibrium?
No, initially we separate them out. Then we can always have situations where many of them can coexist, can exist simultaneously, and then you will have to discuss that in full detail later on. Okay? Not because one equilibrium because of the other equilibrium. No, because all of these parameters then will work together, and then you will determine what the shape of the new equilibrium state is. Okay? So the wall will slide only if there is a pressure difference on the two sides of the wall, and pressure and the slide of the wall will try to change volumes on the two sides, and that change in volume will be towards equating the pressures on the two sides. So the sliding of the wall will be towards equating the pressures on the two sides. So mechanical equilibrium is guaranteed by equality of pressure. And as soon as the difference is a bit of difference appears between the pressures on the two sides, then the wall will move and volumes will change so that the pressure is again equated. The third equilibrium is what I'm calling here chemical equilibrium. This chemical equilibrium is, at times people are more careful in the use of the word chemical equilibrium. They instead talk of diffusive equilibrium or equilibrium with respect to transfer of matter across the wall. And in this case, the wall will have the properties that, number one, it will be if you want to isolate chemical equilibrium from the other two equilibrium conditions and want to see how this works, then you will say that condition can be created by taking an adiabatic wall and a rigid wall and then permeable wall. Matter could easily go from one side to the other side. Why would matter go? Because matter flow will be due to difference in chemical potential. And again, you will say that chemical equilibrium is therefore guaranteed by the equality of chemical potential on the two sides. Okay? So I've just tried to be very detailed in this description because I wouldn't like you to think that these things are not separable from each other. One can look at these three things separately. One can have laboratory conditions in which these things can be separately looked at, and that these situations would complete the whole picture, and if you leave something out, that will not complete the whole situation. Because of which we should be discussing what is called मैंने पहले बहुत पहले एक दफ़ा डिस्कशन की थी so we should actually include therefore our variables as extensive variables would be S, U, V, and intensive variables are temperature, pressure, and chemical potential. We have already included that. So in a system in which we allow all of these three equilibria to simultaneously exist, then we will need to consider all of these variables. Okay? अगर हम चाहते हैं कि सारी जितनी पॉसिबिलिटीज़ हैं इनकी वजह से इन इक्विलिब्रियम स्टेट्स की वजह से वो सारी एग्जिस्ट करें, तो वी विल नीड टू कंसीडर ऑल ऑफ दीज पैरामीटर्स साइमल्टेनियसली. कॉन्सिक्वेंस क्या है? हमने लिखा था du equal to TdS minus PdV as the basic equation from which we derived other relations. हमें इसको एक्सपेंड करना पड़ेगा और हमें इसके अंदर यहाँ पे प्लस म्यू डी एन ऐड करना पड़ेगा for a system in which we also allow particles to be exchanged, for particles to come in and leave the system. एनर्जी के हैं, बिल्कुल सही कहा. एन जो है वो डायमेंशनलेस है, तो म्यू के अपने यूनिट्स एनर्जी के यूनिट्स हैं. ओके, बिकॉज इस इक्वेशन में हर टर्म के डायमेंशन जो है वो एनर्जी की है. अब उसकी वजह से we have therefore something which also, because of this, we know that mu equal to, we can write as partial differential of u with respect to n in the situation when entropy and volume are kept constant. I had not yet written any expression for chemical potential mu. The chemical potential mu is partial derivative of internal energy with respect to n when entropy and V are kept constant. तो जिस तरह दूसरे इंटेंसिव पैरामीटर्स प्रेशर और टेम्परेचर हमने U के डेरिवेटिव्स से निकाले थे, वैसे केमिकल पोटेंशियल भी इसी डेरिवेटिव से. और उसके लिए हमें एक फंडामेंटल इक्वेशन हमें चाहिए होगी जो कि इस तरीके से एक्सटेंसिव पैरामीटर्स के दरमियान एक रिलेशनशिप हो. ऑलराइट, मगर इसके साथ साथ ये अकेली इक्वेशन नहीं है. हमारे पास एक जो उसके बाद दूसरी इक्वेशन है वो H की इक्वेशन है. और H की इक्वेशन में आपको मालूम है कि H और U में जो फ़र्क है वो सिर्फ ये है कि वॉल्यूम और प्रेशर का रोल चेंज हो जाता है, तो इसका रोल चेंज नहीं होता. सो दिस रिमेन्स एज इट इज़. इनका रोल चेंज हो जाता है और इनका रोल चेंज होने की वजह से यू विल हैव dP मल्टीप्लाइड बाई V और फिर साइन भी चेंज हो जाती है. सो यू विल हैव देयरफॉर प्लस V dP और फिर म्यू डी एन. अब उसकी एक्सटेंशन होके इट विल बी, हमने पहले ये लिखा था, नाउ वी विल राइट इट इन एडिशन टू इट विद दिस टर्म. इसका मतलब ये हुआ कि म्यू कैन ऑल्सो बी डिफाइंड एज पार्शियल डिफरेंशियल ऑफ H with respect to n, but this time keeping entropy and pressure constant. यहाँ पे entropy and volume was kept constant, यहाँ पे entropy and pressure is kept constant. और अगर नेक्स्ट एक्सप्रेशन को देखें तो हमने F फ्री एनर्जी, हेल्महोल्ट्ज़ फ्री एनर्जी के लिए लिखा था एक्सप्रेशन. वो U से हमने लिया था, जबकि T और S का आपस में रोल हमने इंटरचेंज किया था. U और हेल्महोल्ट्ज़ फ्री एनर्जी में जो फ़र्क है वो सिर्फ यही है कि T और S का रोल चेंज हो जाता है. अगर T और S का रोल चेंज हुआ तो इसका मतलब ये हुआ कि वी विल हैव S dt टर्म, और चूंकि यहाँ प्लस है तो विद अ माइनस साइन, सो यू हैव माइनस S dt माइनस PdV plus mu dn. ठीक है ना? इसका मतलब ये हुआ कि mu can be defined as partial differential of f with respect to n, and now you keep T and V constant, volume and temperature constant, और आखिर में dg था माइनस s dt प्लस v dp प्लस mu dn. उसमें u के हिसाब से दोनों वेरिएबल्स, दोनों टर्म्स के अंदर वेरिएबल्स का इंटरचेंज था, तो दोनों के अंदर चेंज है, साइंस भी चेंज हो गई. और फिर mu gets defined as partial differential of g with respect to n when you keep T and P constant, temperature and pressure का. तो mu को आप किसी भी एनर्जी फंक्शन से के डेरिवेटिव से डिफाइन कर सकते हैं. यहाँ पर फर्क जो है वो ये कि उनमें किस किस्म की फिजिकल कंडीशन के अंदर आप ये कर सकते हैं. ये दो जो हैं वो एडियाबैटिक कंडीशंस में हैं. एक केस में एडियाबैटिक एंड वॉल्यूम केप्ट कांस्टेंट, दूसरे केस में एडियाबैटिक प्रेशर केप्ट कांस्टेंट. ये दोनों जो हैं उसमें आइसोथर्मल कंडीशंस में हैं, लेकिन एक केस में वॉल्यूम केप्ट कांस्टेंट, दूसरे केस में प्रेशर केप्ट कांस्टेंट. So this way you define your chemical potential depending upon the physical situation in which you are determining chemical potential. ठीक? Okay. तो एक तो ये बात है. दूसरी ये है कि म्यू को इंक्लूड करने से आपको थोड़ा सा और भी relationship में extension है. I could leave these extensions to you to work out yourself, लेकिन मैं थोड़ा सा इसमें I would like to do them over here so that you see how things are going. अगर हम फर्स्ट के यहाँ से हमने याद होगा कि जब हमने लिखा था कि du equal to TdS माइनस PdV, हमारी स्टार्टिंग इक्वेशन हमेशा यही होती है ना. तो जब ये लिखा था तो यहीं से हमें एक मैक्सवेल रिलेशनशिप मिली थी. dt by dV at constant entropy is equal to d minus dP by ds at constant volume. ठीक है ना? इसी एक्सप्रेशन से हमने ये मैक्सवेल्स रिलेशन लिखा था. राइट? अब अगर हमारे पास du की इक्वेशन ये नहीं है बल्कि साथ में म्यू dn भी है, तो does it allow us to write a few more मैक्सवेल्स रिलेशंस? अगर इन दो से आपको ये मिल सकता है तो इनमें से किसी एक को कांस्टेंट रख के बाकी के साथ आप म्यू के साथ मिलाकर यू कैन राइट डाउन इक्वेशंस. यहाँ पे आपको चेंज करना चाहिए. यहाँ पे आपको n कांस्टेंट यहाँ पे और n कांस्टेंट यहाँ पे करना चाहिए. पहली बात तो ये कि सिर्फ s और v ही कांस्टेंट नहीं है बल्कि n भी कांस्टेंट है इसके अंदर. और उसके साथ साथ आपको easily you can see that dt by dn, अब मैं इसको इंक्लूड करके एक मैक्सवेल्स रिलेशन लिखना चाह रहा हूँ. सो प्लीज ज्वाइन मी इन गेसिंग कि अब क्या टर्म होगी इसके साथ. आई विल कीप द अदर वेरिएबल्स कांस्टेंट है. सो आई विल टेक s and v constant, and this will be equal to d mu by I will keep v constant and n constant. Okay, so this is a new Maxwell's relation that I have obtained by taking v to be constant and then use the same method that I used earlier to get this relationship from these two additional terms, and I got this. And correspondingly, for this constant term to be 0, I put V constant here and V constant here. चलिए नेक्स्ट बताएं क्या होगा. dp by dn माइनस बाहर लगा दूं पहले से मैं, माइनस dp by dn at constant s and v equal to and because of mu I will have n constant here, and before that I am keeping s constant, so s is constant. Okay?
ये भी अब रूल है कि p और n आए तो माइनस लगाना.
Now you will have to, these are things that you will try and make rules for yourself. Well, not rules, but mnemonics for yourself. आपको ये और भी लिखकर देखने पड़ेंगे. मिसाल के तौर पे नेक्स्ट वन इज व्हेन यू राइट dh equal to TDS plus VDP plus mu dn. अगर यहाँ से एक तो आपके पास पहले से मौजूद होगा जो पहले से था, अगर आप यहाँ से बनाना चाहेंगे तो आप बनेगा dt by dn at constant s and p equal to d mu by ds at constant n and p. और उसके बाद वाली टर्म होगी dp by dn at constant volume and entropy is equal to partial differential of u with respect to volume when you keep. क्या हुआ? गलती कर दी मैंने. यहाँ पे कहाँ पे dv बिल्कुल सही कह रही, बिल्कुल सही. ओके you are right. dv by dn, and therefore over here I will have p and s, and here I will have d mu by dp, and this will be when n is kept constant and s is kept constant. तो यहाँ पे you still didn't have any p and n in the same bracket, so we will need to check somewhere else. वो जो होगा वो मेरा ख्याल है कि it will come in df. df is minus s dt minus p dv plus mu dn, and if I write now d minus dp by dn at constant volume and temperature, this is where I'll keep temperature constant, and this is equal to mu d mu by d v at constant temperature and n. Constant volume and at constant temperature. Constant temperature and n. So you're right. In this case, it comes out that whenever there are p and n in the same bracket, there is a minus sign coming out. I have left out plus 3 more such relations. And these relations shouldn't be, they're not as simple and straightforward as they were without the third term. But still, they follow a pattern, and that you might like to write them down and look at it for a few minutes to understand कि ये चीज़ें कैसे हो रही हैं. Okay. I am now going back to the we have spoken of the state of equilibrium, and and we need to also understand how state of equilibrium is related to entropy. And we have already noted down that in a spontaneous process, the system goes to a state of higher entropy. Right, we always said that delta S is a positive quantity. If you let the system go on its own, spontaneous process on its own, you don't work on it, you just let it go wherever it wants to go in a spontaneous manner, then the system will go to a state which will have higher entropy than the previous state, and if it cannot find a state of higher entropy, it will simply not change. It will stay where it is. Okay. And suppose when you, in a spontaneous process, there are many states that are accessible to the system. Among all the states available to the system under any given conditions, under the given conditions, मेरे पास मैं इसको ऑफ करना भूल गया है. Under the given set of conditions, not condition but set of conditions, among all the states available to the system will go to the state with the highest entropy. So the system is originally over here and it can go to this place or this place or this place or this place. It could go to any of those states. It will choose, it will spontaneously go to the state which has the highest value of the entropy. So the first condition is a milder condition, the second condition is a stronger condition. It is not going to go to any state which has a higher entropy. It will go to the state, among all the possible states, it will go to the state which has the highest value of entropy. And that will be so the state of equilibrium is the state of highest entropy. Again, I should put in the bracket the same statement that I put up above, that under the given conditions of whatever conditions you have of volume, conditions on volume and conditions on energy and so on and so forth. So this is actually defines the state of equilibrium. The state of equilibrium is the state of the highest value of entropy among all possible states that are available to the system. And if you want to consider the state of equilibrium, then on the basis of this criterion, it is characterized by two things: maximum entropy. Maximum entropy means that, if suppose you plot entropy and you find that entropy is maximum at this particular point, then this is the point which has two properties. Number one, ds equal to 0, and number two, d2s is positive. Is it positive or negative? d2s is positive. नेगेटिव होगा मैक्सिमम के लिए. मैं गलत लिख गया हूँ अपने पास पे यहाँ पे. d2s is d2e is positive. You're right. Okay. मैं अपने पास यहाँ पे गलत लिख गया. Simultaneously,
इस स्टेटमेंट से हम ये कह सकते हैं the most stable state is the state of isolation.
So इनका क्वेश्चन जो है वो ये है कि जहाँ हमने लिखा हुआ है कि state of equilibrium is the state of highest entropy, so he is asking if one can also say that the most stable state is the one which has the highest value of entropy, right? Okay, yeah, sure.
So तो इसमें जो अभी आप एग्जांपल दे रहे हैं, फर्ज करेंगे वही बाउल है और उसके ऊपर बॉल रखी हुई है, तो हमारे पास दो स्टेबल स्टेट नहीं आते.
Now, do not confuse the plot that I am drawing over here. This is that of entropy. Over here, I have entropy as a function of maybe U, maybe V, or whatever, or V, or whatever. And therefore, this is the situation of maximum. The other condition that I'm about to tell you is that on energy for a state of equilibrium. इसके बाद जो उसके बाद की का पॉइंट है वो ये कि in a spontaneous process, system, any system, a system goes to a state of lower energy. Okay? ये तो हमारे ऑब्जर्वेशन में है, ये तो कोई नई बात नहीं है. System always goes to a state of lower energy. If you leave the system to itself, it will go to a state of lower energy. And so हमने वहाँ पर लिखा delta S is positive, यहाँ पे delta U is negative. It goes to a state of lower energy. UF is smaller, is larger than, is smaller than UI. Okay, and delta U is UF minus UI. And among the accessible available states, the system will go to a state of lowest energy. The state of lower energy, the state of lowest energy.
Sir, like a system goes to a state of lower energy. So doesn't lower energy corresponds to a lower entropy?
No. Lower energy state doesn't. Lower energy doesn't mean lower entropy. No. Entropy and energy are completely independent variables. That is why we write our fundamental equation as a relationship between U, V, and S and so on. So these are like, in your coordinates you have X and Y and Z. And you can't say that Z depends upon X and this will be what.
So मैं इसीलिए कहता है कि हम U को कहते हैं कि U S V और N पे डिपेंड कर रहा है, तो U कम हो रहा है तो ये नहीं correspond कह सकते कि.
No, and then there is this equation which determines the equation. For example, I was just about to take this example of your X, Y, and Z coordinates being independent variables, right? But you can always find an equation among them, right? Like an equation for a straight line and so on. You can find an equation for them, and that equation will relate X, Y, and Z. But that will define a specific situation, will be the state of the system, right? Similarly, over here, your U and S and V and N are the basic variables, independent variables, and then there will be a relationship among them, which will be called fundamental equation. This is what we have called fundamental equation. And that fundamental equation will be in a space spanned by these four variables.
So would that type of condition also apply on energy, like the condition of derivative being equal to zero?
Derivative? Sure. I was about to write this condition that this lowest energy, and therefore the state of equilibrium is a state for which du is 0 or d2u is a positive quantity. It is a minimum energy. Okay?
So how is it possible that the most stable state is the state with the
maximum disorder? Okay. Now, the question is that of the states that are available to the system. And if the choice before the system is to go to a state of disorder, it will go to a state of disorder. If there is no choice for it to go to a state of disorder, it will not go to a state of disorder. All right? On its own. And therefore, this question should be, in terms of these variables, this is the starting point. You can enter into a very good discussion on how come many things happen before us which are actually in an ordered state. For example, a plant grows, a plant is an ordered thing, or a virus comes into being, a new virus comes into being, which is an ordered element, and this is something which happens spontaneously, all right? Yet it is something which is a state which is happens under very specific conditions, and those conditions will have to be taken into account. So if I were to, put this in a very simple picture, hopefully you have a couple of more minutes, patience for a couple of more minutes. If I were to write over here, Haji, 15 मिनट ले सकता हूँ मैं? ओके, कल जो मैंने 15 मिनट दिए आप लौटाएंगे वो मुझे आप. Very good, very good. Suppose I were to take this picture, and I can think of this as a space which has S and U and V. I can't make a 4-dimensional space, वरना मैं N की भी बना देता हूँ space. अब इसमें I can think of a surface which now I don't know how to make that surface, but suppose I were to create a surface of some kind over here, okay, and this is a surface in this space, and in this surface if I were to take saying that if I put a condition that energy has to be this, this is the value of energy, and then on this energy it will only take up that, it will go to that state which has the highest value of entropy. It won't be, in any of the, you see, every point on this sphere, on this surface would be a fundamental equation, would be an equation of the system. And then we will say that, look, it has to be for this value of energy, or this value of volume, for example. Then for this particular value of volume, only so many states are available, and among those states it will go to the state of highest entropy. Similarly, I can also say that for that set of volume and number, it will go to the minimum, this much value of energy. So that will be those will be the states available to it, and that is how the system equilibrium states will be determined. Okay, and among them, the highest entropy state may not be a disordered state. It may only be a state with increased entropy. That's it. Because the conditions will determine what will be the state of entropy and which state will have the highest value of entropy among the possible states. Okay? I will spend more time on this later on. Okay? You see, these are new concepts on which I need to make sure that you are very clear.
आप इसमें जब भी आप कंसिडर कर रहे होंगे तो इसमें आप दो चीज़ें देखेंगे ना, यू और एस साथ एक साथ.
Exactly.
तो मुझे कैसे पता चलेगा कि एक ही टाइम पे म्यू यू